Hello students, in the previous lecture we have defined a subgroup. For any subset of a group to be a subgroup, uh, the subset must satisfy all the four axioms of the group. And for any subset to be subset of a subgroup to be subgroup, uh, the binary composition of both the group and subgroup must be same, right? So this is a conclusion of this. Now we'll try some lemmas. Lemmas to show for any subset to be a subgroup of group. Lemma is a theorem which has no relevance to previous study, but will be used in the for this study. Lemma is a theorem which has no relevance to previous study, but will be used in the for this study. Lemma will for two binary composition will prove the lemmas for the one binary composition and for multiplication, and you will prove them for the addition. Lemma same lemma for the addition binary composition. Now let's prove first lemma of binary composition multiplication. A non-empty subset H of a group G is a subgroup if and only if uh, for all A into B belong to H, for all A belong to H, and A inverse belong to H for all A belong to H. Means we are given that any non-empty subset H of a group is a subgroup if and only if closure and inverse element exist. If closure property holds in a subset and inverse element of subset, then H is such a subgroup. Or if H is subgroup of a group G, then closure property and inverse element implies that subset is subgroup. Proof of this is necessary part. Let's assume that let's suppose that non-empty subset H of a group G is a subgroup. Is a subgroup. The subgroup. Uh, our aim is to show, therefore, H itself is a let let us suppose that H is a non-empty subset of a group G is a subgroup. This is given. Our aim to show closure and inverse element exist in H. Now, therefore, H is itself a group. Definition of subgroup. If H is a subgroup means H is itself is a group. Means H. If G satisfies all the four axioms, closure, associative, inverse element, and identity element for the element of G on the basis of multiplication, then H also satisfies all the four axioms. Therefore, inverse element and closure property rules in this. Therefore, H is a subgroup of first implies first and second holds true implies this. Closure and inverse element is in H. Therefore, like that. Now, section part. Suppose that H is a non-empty subset of G such that closure and identity inverse element exists. Our aim is to show H is a subgroup means we have to show that associative law and identity element exists in H. Closure and access identity element to hold in H is given. To prove is H is itself a group. Our aim is to show that associative law and identity element exist in H. So as for associative law, now A, B, C belongs to H. H is a subgroup subset of G. So A, B, C also belongs to H. H is a group. Therefore, associative law hold in H, hold in G. Sorry. So A, B, C element of H. So associative holds H. Therefore G. So associative hold in G. Therefore associative law hold in H also. Existence of identity element in H. By second condition, A inverse belongs to H for all belongs to H. It is given. So A into A inverse closure property. First, A into A inverse belongs to H. A into A inverse is equal to E because A H is a subset of G. So all the elements of H are elements of G. G is a group. Therefore, A into inverse, A and A inverse also belongs to G, and A into inverse is equal to E, the identity element in G. So this is also identity element of H. Element H implies E is the identity element of G. This is the E element of H, and H is itself a group. Like H is a subset of G, and H sets all the four axioms. Closure, inverse element, identity element, and associative law. Therefore, that's a subgroup. Similarly, you can prove for the biquestrian addition. The next lemma is a non-empty subset H of a group G is a subgroup if and only if A, B inverse belongs to H for all elements H. Now both axioms combined. The first lemma, both axioms combined. Inverse element is here, closure inverse both here. So the first lemma is a refinement from first lemma. So now necessary part again. A non-empty subset H of a group is a subgroup. Subgroup is given. Our group A, B inverse belongs to H for all elements. So uh, let us suppose that a known subset H of a group G is a subgroup. Okay, subgroup means H is itself a group, means H has all the four elements. Our aim is to prove for all A belongs to H, A belongs to H. Now A belongs to H, H is a group, so A, B also belongs to H, belongs to H. B belongs to H, therefore B also belongs to H. So A and B belongs to H. Now closure property, H is a group, H is itself a group. So A, B also belongs to H. Now substitution part. Suppose that a non-empty subset H is known subset of G, so that for all A belongs to H, A belongs to H. Now our aim is to show H is subgroup. Subgroup means H is subset. So now again associative law. Now let A belong to H, a subset of G. So A belongs to G. G is a group. Therefore, associative law holds in a group. Therefore, A belongs to G. But A also belongs to H. So associative law holds in H also. ABC also belongs to H, therefore for ABC belongs to G, this is the whole, therefore ABC belongs to H, therefore AC belongs to H. Existence of identity elements. For all A belongs to H, A and A also belongs to H. You can write it this way. For all A belongs to H, A and A belongs to H. So now A into, if A belongs to H, A B also belongs to H. So A to A naught is equal to A and H is subset of G and G is a group. Therefore, A into A inverse is equal to E. E is the identity element of G. Therefore, identity element of also E inverse. Now, catch means A inverse is equal to E identity element. So, associative identity. Now, existence of inverse. E belongs to H. We have shown E belongs to H, and A also belongs to H. A into A. We are given that. If A and E belong to H, E inverse E and A belong to H. So for the given condition, A inverse also belongs to H. A into inverse is equal to A inverse also belongs to H. Inverse belongs to H. So inverse also belongs to H. Now closure property. A belongs to H. A B also belongs to H. Inverse of every element exists in H. Okay. So now, if A and B also belongs to H, therefore A B inverse from given condition. Right? So AB nodes also said so AB nodes also therefore AB B nodes is equal to B. So this applies H have a element sugar holes no cell exists and closure goes to the H. Now next lemma is for the final set. So the first and second lemma we have proved for addition and for multiplication you prove them for addition similarly. A non-empty finite subset H of a group G is a subgroup if and only if closure property hold if and only if closure property holds in H for all infinite H. Now this is the part again. This part A, let a non-empty finite subset H of a group G is a subgroup. Therefore, H is a central group. H group a group for all AB belongs to H. A into closure property holds. That is a group or the whole can hold true. Therefore, H is a group. Now substitution part. Substitution part A. Suppose that H is a finite, non-empty finite subset of G, group G, such that for all A belongs to H, closed group will hold H. Now our aim is to show that our binary composition here is binary composition multiplication is H. Our aim to show this is a H is a subgroup. Let's show H is a group. So for all associated, for all A belongs to H, implies H is a subset of G. So H is group G. So G is a group, so H should be holds in G, therefore H should be holding in G. Now, those are given H should be holds. Using theorem, every finite semi-group is a group if and when both the cancellation of holds in group. Using the theorem, every finite semi-group is a group if and only both the cancellation of holds true in it. Now our aim is to complete the proof. We now in order to complete the proof, we will prove that both the cancellation are hold in H. So let us let cancellation happen. Let A be equal to H such that A B is equal to AC. Since A belongs to H, so A belongs to G. So G is a group. So A also belongs to G. So A such that A into inverse is equal to E is equal to A into inverse. Because A belongs to G, so A belongs to H. Since A belongs to H, A also belongs to G. Now, now, uh, now we know that AB is equal to AC, H is same group, so uh, we multiply by inverse this equation by inverse. Now, using the shifted law, inverse the E to inverse is equal to E, inverse is equal to E, is complete. For the addition law, we both multiply by inverse on both sides. We got this. So left law and cancellation law in the same group. In the same group in which semi group in which closure property hold true in format cancel it hold true. That is the group. So it's G.